China is reportedly producing more quantum computing research papers than any country in the West, more than the United States, more than the entire European Union combined by most bibliometric counts. That is the kind of statistic that usually signals the next technology era is already written, except that the country currently leading on independently verified, deployed quantum hardware results is not the one leading the publication tables. Before you file this as either a triumph or an irrelevance, the honest answer is that nobody is certain which currency matters more right now, papers or machines. And that uncertainty is not a failure of analysis, it is the actual shape of the bet. The stakes are real. Quantum computing's fault tolerance era is approaching a threshold where early decisions about talent, architecture, and research depth become very difficult to reverse. Getting the leading indicator wrong now has decade-long consequences. By the end of this, you will understand what publication dominance actually measures, why the paper-to-machine conversion rate is the number nobody publishes, and which of two genuinely defensible bets on the future is better supported by the evidence we actually have. This is not really a story about who writes more papers. It is a story about whether a country can raise its research floor high enough to eventually move its own hardware ceiling, and whether that is even how quantum breakthroughs happen. Start with what is being measured. China's publication lead, reported across multiple bibliometric analyses, reflects sustained national investment in quantum research capacity. Universities, laboratories, graduate programs producing a broad and deep talent pipeline measured in researcher years, not headline results. That investment is real. The output is visible. By most counts that include both peer-reviewed journals and preprint servers, China's share of global quantum computing research is the largest of any single nation. But here's what a publication count actually captures, and what it misses. Think of it like measuring a city's construction activity by counting every permit filed. It tells you how much is being built, but not whether any of it is load-bearing. One well-placed support beam does more structural work than 50 decorative panels. Both show up the same in the permit log. Publication counts bundle peer-reviewed experimental results, theoretical proposals, and preprints indiscriminately. A country can lead the count by producing many narrow confirmations of existing theory rather than the few deep results that change what hardware can actually do. And the honest hedge on the publication claim itself, the exact magnitude of China's lead varies depending on whether preprints are included and how field boundaries are drawn. The lead is real. How large it is depends on the methodology, and that methodological question matters for evaluating what the lead means. So volume can be gained by quantity, but volume is also how talent pipelines are built. Graduate students writing papers today are the same people who will build the machines a decade from now. The question is whether this particular field rewards breadth or depth at the decisive moment. And that question has a specific answer shaped by where quantum computing is right now. Fault-tolerant quantum computing is not a gradient. It is a threshold. Below it, every improvement just makes the system less noisy, useful for research, not commercially transformative. Above it, you have error-corrected systems where adding more qubits makes the machine more powerful rather than more chaotic. That is the crossing point the entire field is building toward. Before it, you have research tools. After it, you potentially rewrite drug discovery, material science, and the cryptographic security that underpins global finance. Think of it as the moment a bridge stops swaying and starts holding load. And before that point, every improvement just makes it sway a little less. After it, you can drive trucks across. The entire field is building toward that crossing, and the construction decisions you make on the wrong side are very hard to undo on the right side. In 2024, Google's Willow chip produced a result that moved this conversation. Error rates fell as qubits were added. That is below-threshold error correction scaling, published in Nature, and independently reviewed. It means the system was not just getting better, it was getting better in the specific way that points toward fault tolerance. That result is the current high watermark of publicly verified, deployed quantum hardware capability. And it came from a United States affiliated lab, not from the country leading the publication tables. By the public record, China has not produced an independently verified hardware result at the capability level of the Willow demonstration. That absence is stated carefully. Non-public results may exist and cannot be claimed or denied. But by what the field can actually see and verify, the hardware milestone lead sits with United States affiliated labs, and the publication lead sits with China. Both facts are simultaneously true. They do not cancel each other out. They sharpen the question. Now look at the mechanism. In most technology fields, publication volume is a reasonable leading indicator because progress is roughly continuous. More inputs produce more outputs over time. Quantum hardware is different. The results that have actually moved the capability frontier have come from focused teams pursuing specific architectural insights and specific error correction approaches, not from the broadest research base. The Willow result came from a focus group. IBM Quantum's hardware milestones came from sustained institutional focus. These were depth bets, not breadth bets. That is Bet B's strongest argument. It runs like this. Quantum progress at the capability frontier is threshold sensitive, not volume sensitive. The breakthroughs that matter are produced by a small number of deeply funded, experimentally focused teams drilling into the specific problems that fault tolerance requires. A wide river covers more ground and feeds more tributaries. A deep drill hits the resource, and in quantum, the question is whether you need the river to find where to drill, or whether you can just drill where the geology already points. Bet A's counter is serious. Those focused teams do not operate in a vacuum. The ideas that become hardware breakthroughs are usually visible in the published literature years before they become machines. A country generating more of that literature has a higher prior probability of generating the next threshold insight if the quality distribution of its output holds. The floor being raised is the ecosystem from which the drills eventually emerge. Which model is right? The honest answer is that the evidence does not settle it, and here's the specific gap that makes it unsettled. The paper-to-machine conversion rate, meaning the fraction of quantum papers that contribute to independently verified hardware milestones, is not a published metric. Nobody tracks it. That absence is itself informative. The field does not yet have a good instrument for measuring research efficiency, only research volume. This is the number nobody publishes, and its absence means both bets are flying partially blind. What we can say with precision, the publication lead is real by most bibliometric counts, though its exact magnitude depends on methodology. The hardware milestone lead is independently verified and sits with the United States affiliated labs. A significant portion of China's quantum publications are believed to be theoretical or simulation-based rather than experimental hardware results, though the specific proportion is not a published figure. And if that proportion is substantially higher than in Western output, the floor being raised is partially abstract, valuable for the talent pipeline, less directly connected to the experimental insights that actually move hardware. The strongest real limitation on the hardware lead argument runs the other direction. Independently verified hardware milestones are a lagging indicator. The research that produced today's milestones was typically conducted years earlier by a general pattern in deep tech development. Today's Chinese publication volume may be the input to hardware milestones years from now, and we do not have the instrument to measure that pipeline cleanly. The pattern this story fits is not unique to quantum. In semiconductors, Japan outpublished the West on research for years, while Taiwan and South Korea outmanufactured it. In physics, the Soviet Union produced world-class theoretical work, while the United States converted it into hardware faster. Publication dominance is a floor, not a ceiling. A higher floor is genuinely valuable. More people who understand the problem, more chances of generating the insight that matters. But historically, in analogous deep tech fields, it does not automatically become a ceiling. Stated carefully, this is a historical pattern, not a deterministic law for quantum specifically. The quantum record is too short to treat any analogy as settled. Here's my honest read. The two extremes to reject. Triumphalist are, China's publication lead means it will dominate quantum computing. Ignores the conversion gap and the current hardware deficit that is clearly visible in the public record. Dismissive, paper counts do not matter. Only machines do. Ignores that machines come from people who wrote the papers years earlier and that a research base this wide is building something real over the long horizon. The honest position is that China's publication lead shifts the long horizon odds without touching the near-term hardware race. Those are two different things. The near-term race to fault-tolerant hardware remains with the labs that are already drilling deep, by the evidence that exists right now. The longer horizon question of where the next decade's experimental talent comes from is genuinely open. Anyone who collapses that distinction is selling you confidence they do not have. China is raising the research floor of quantum computing faster than any country in the West. The floor is real. The question that the evidence cannot currently answer is whether the hardware ceiling moves because someone raises the floor beneath it, or whether ceiling moving in this specific field requires a different kind of force entirely. fewer papers, more focused bets, more experimental depth pointed at the specific threshold the field is approaching. That gap between floor and ceiling is where the next decade of quantum competition actually lives. So here's what I want your honest read on in the comments. Do you think raising the research floor is how quantum ceilings eventually get moved? Or is this a field where the ceiling only moves through focused drilling, regardless of how wide the foundation underneath it is? Both sides have real evidence. I want to know which one you would actually bet on. Subscribe if you want to follow how this bet resolves. When China's publication depth either shows up in hardware milestones or does not, that is exactly what this channel tracks. China is writing more of quantum's future than anyone in the West expected. Whether the writing becomes the machine is still the bet.